Chapter 1.2, Reflections and Stretches. Reflection is a transformation that reflects or flips a graph about a line called the line of reflection. It can change the orientation of a graph, but not its shape. Vertical reflection. Compare the graphs of y equals f of x to y equals negative f of x. Consider the function f of x equals x squared. Use your graphing calculator to compare the graphs of y equals f of x, which is y equals x squared in this case, and y equals negative f of x, which would then be y equals negative x squared. Sketch the graphs. So using our graphing calculator, we can graph x squared, which gives us this. We can also make a table of values to help us plot some points. For y equals x squared, we have x values, y values. Let's go -3 to 3 for the x values. -3 squared is +9. -2, -2 squared is +4. -1, -1 squared is +1. 0, 0 squared is 0. 1, 1 squared is 1. 2, 2 squared is 4, and x equals 3. 3 squared is 9. So at x equals -3, we have a y value at +9. At x equals -2, we have a y value of +4. X equals -1, we have a y value of 1. X equals 0, we have a y value of 0. When x is 1, y is 1. When x is 2, y is 4. And when x is 3, y is 9. We can join those points with a curve to get our parabola. Then we want to graph y equals negative f of x. So go back to y equals, go down to y2 and put in negative x squared. Graph that. And what we should notice is that it's the same as y equals x squared, just been reflected down across the x-axis. We can do a table of values to plot some points. We'll do the same values that we did on in the other function, -3, -2, -1, 0, 1, 2, and 3. -3 squared is +9, and then times -1 is -9. -2 squared is +4, times -1 is -4. -1 squared is +1, times -1 is -1. 0 squared is 0, times -1 is still 0. 1 squared is 1, times -1 is -1. 2 squared is 4, times -1 is -4. And 3 squared is 9, times that by -1, and we get -9. So when x equals -3, we have y equal to -9. When x is -2, we have y at -4. When x is -1, we have y equal to -1. When x is 0, y is 0. When x is 1, y is -1. X equals to 2, y equals to 4. And when x is 3, y is -9. And then we join those points together with a curve. And we get our parabola y equals -x squared. And this one was y equals x squared. How does the graph of y equals negative f of x compare to the graph of y equals f of x? It's the same shape. But reflected across, or you can also say about or over the x-axis, which is a vertical reflection. If point xy lies on y equals f of x, then the coordinate of point y equals negative f of x is, the y values were affected, the x values were all the same, but the y values became negative y, so it becomes x negative y. So when you have a vertical reflection, you replace the y values with negative y. What do you notice about the point 0, 0? The point 0, 0 doesn't change. With reflection, it's still 0, 0. Invariant point is a point on a graph that remains unchanged after a transformation is applied to it. Any point that lies on the line of reflection is invariant. So we can say that the point 0, 0 is an invariant point. Horizontal reflection. Compare the graph of y equals f of x to y equals f of negative x. Example, consider the function f of x equals the square root of x. Use your graphing calculator to compare the graphs of y equals f of x and y equals f of negative x. So y equals f of x in this case is y equals the square root of x, and y equals f of negative x would be y equals the square root of negative x. Let's start by graphing f of x, which is the square root of x. And here's what we get. I don't think this calculator will show my x-intercept, but that's okay. We can also do a table of values for f of x equals square root of x, x and y. We can't have the square root of a negative, so we start at x equals 0, then do 1, then do 4 because it's a perfect square, and 9 because it's a perfect square. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. We can plot those points, 0, 0, 1, 1, 4, 2, and 9, 3. Join those points with a curve, and there is our function y equals square root of x. Next, y equals the square root of negative x. Let's go back to our y equals. Go down to y2 and enter the square root of negative x. Graph that, and this is the function we see. We can also do a table of values for this one. F of negative x, which equals the square root of negative x, x and y. We can't have negative under the square root, so if I put 1 for x, then because it's negative x, that would become negative 1. So I want to actually put in negative values, so I'm going to start with negative 9. Then that gives us the square root of negative 9, which equals the square root of 9, which is 3. Then negative 4 is the square root of negative 4, which is the square root of 4, which is 2. And negative 1 would be the square root of negative 1, which is the square root of 1, which equals 1. And then 0, square root of 0 is 0. Plot those points. We have 0, 0, negative 1, 1, negative 4, 2, and negative 9, 3. And then we join those points together, and that's the graph of our function y equals the square root of negative x. How does the graph of y equals f of negative x compare to the graph of y equals f of x? The graph of y equals f of negative x is the same shape as y equals f of x, but it is reflected across or over or about the y-axis, which is a horizontal reflection. If a point xy lies on y equals f of x, then the coordinate point on y equals f of negative x is, the x value is affected here, the x value became negative of what it is in f of x, so we get the point negative x, y. So when you have a horizontal reflection, you replace the x values with negative x. State the coordinates of any invariant points. What point was the same before and after the reflection? That would be the point 0, 0. 0, 0 is the same before and after the reflection. So it is an invariant point. And the reason it's an invariant point is because it lies on the line of reflection. Our line of reflection is the y-axis. And the equation of the y-axis is x equals 0, so on the y-axis, or you can say on the line x equals 0. That's our line of reflection. Any point of the original function that is on that line is an invariant point and will be in the same location after a reflection. A summary of reflections. For the function y equals negative f of x, the transformation from y equals f of x is a reflection in the x-axis. We can also say this by saying across the x-axis or over the x-axis or about the x-axis. All of those would be equivalent. Mapping notation, a point on the original function xy becomes the point x negative y for y equals negative f of x. And an example, f of x is a quadratic opening up in this case, and then y equals negative f of x is the reflection of that across the x-axis. So now it's a quadratic opening down. Y equals f of negative x is a reflection in the y-axis. Again, you can say instead of in, you can say across the y-axis, you can say over the y-axis, or you can say about the y-axis. Mapping notation for y equals f of negative x, a point xy becomes negative xy for y equals f of negative x. And then we have an example. Quadratic y equals f of x is here. It's shifted to the right so that the vertex is in quadrant 4. When we reflect that across the y-axis, then we have the vertex of the quadratic still opening up, still the same shape, but the vertex is now located in quadrant 3. Stretch, a transformation that changes the shape of a graph and makes it look wider, narrower, taller, or shorter. Vertical stretch. Compare the graph of y equals f of x to y equals a times f of x. Example, consider the function f of x equals the absolute value of x minus 4 minus 2 shown below. Sketch the graphs of y2 equals 4 times f of x and y3 equals 1/2 times f of x, and complete the table of values for both. We have a table of values here. We've got our x values and then the y values, which would be f of x, the values of f of x. Then we have y2, that's going to be our y values for the y2 function, which is 4 f of x. And then we have y3, which are the y values for the third function, 1/2 times f of x. Let's calculate the y values for y2. We're multiplying the y values from y equals f of x by the a value, which is 4, to get the values for y2. 2 times 4 is 8. 0 times 4 is 0. Negative 2 times 4 is negative 8. 0 times 4 is 0. And 1 times 4 is 4. Let's plot those points. When x equals 0, y2 is 8. When x is 2, y2 is 0. When x is 4, y2 is negative 8. When x is 6, y2 is 0. And when x is 7, y2 is 4. Then we can join our points together. And this is our function y equals 4 f of x. For y equals 1/2 f of x, we want to multiply the y values from f of x by 1/2. 2 times 1/2 is 1. 0 times 1/2 is 0. Negative 2 times 1/2 is negative 1. 0 times 1/2 is 0. And 1 times 1/2 is 1/2. Plot those points. When x equals 0, y3 is 1. When x is 2, y3 is 0. When x is 4, y3 is negative 1. When x equals 6, y equals 0. And when x equals 7, y equals 1/2. We can join our points. And then we have the graph of the function y equals 1/2 f of x. State the coordinates of any invariant points. What points are the same on all three graphs? That would be the x-intercepts at x equals 2, y is 0 for all three functions, and when x equals 6, y is 0 for all three functions. 2, 0, and 6, 0 are invariant points. What makes them invariant points? They stay the same after transformations. Describe how the graphs of y2 equals 4 f of x and y3 equals 1/2 f of x compared to the graph of y equals f of x. y2 has y values 4 times larger than y equals f of x. Making the graph of y2 taller and more narrow. y3 has y values that are 1/2 times as big as y equals f of x. Making the graph of y3 shorter and wider. If a point xy lies on y equals f of x, then the coordinate point on y2 equals 4 f of x is x and then 4y. And the coordinate on y3 equals 1/2 f of x would be x and then 1/2 y. Is y over 4 equals f of x the same as y equals 4 times f of x? For y over 4 equals f of x, we can move the 4 to the other side of the equals by multiplying both sides by 4. Then 4 divides out here, and we get y equals f of x times 4, which we can write as 4 f of x. So yes, they are the same. So when you have a vertical stretch, you multiply the y values by the a value. Ignore this, that should be on the next page. Horizontal stretch. Compare the graph of y equals f of x to y equals f of b of x. Example, consider the function f of x equals absolute value of x. Sketch the graphs of y equals f of x, which is y equals absolute value of x, y2 equals f of 4x, which would be y equals absolute value of 4x, and y3 equals f of 1/2 x, which would be y equals absolute value of 1/2 x. Use your calculator and look at your tables. Go to y equals, clear what we have there, enter absolute value of x, graph that. To see a table for the function on a TI, we go second graph to get table, and it shows us the table with the x and y values. On a Casio, you go menu and then whichever one says table, depending which one you're using. This one is number 7, and then it shows me the table. Then I can plot some points to draw the graph of y equals absolute value of x. When x is 0, y is 0. When x is negative 1, y is positive 1. When x is negative 2, y is positive 2. X negative 3, y is positive 3, and so on. So we'd have a line going up like this. And then going the other direction, when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. When x is 4, y is 4, and so on. So we have a line going up 1 over 1 to the right. That is the graph of our function y equals absolute value of x. Go back to y equals, go down, enter the absolute value of 4x for y2. Graph that. It's the red graph. It's much more narrow than y equals absolute value of x. We can go to the table and plot some points. So when x is 0, y is 0. I'm looking at the y2, so the red numbers on the right there. When x is 0, y is 0. When x is 1, y is 4. When x is 2, y is 8. And then going the negative direction, when x is negative 1, y is 4. And when x is negative 2, y is 8. You can join those points. That is the graph of the function y equals absolute value of 4x. Go back to y equals, and now graph absolute value of 1/2 x. We get the black line. Go to our table, second function graph on the Casio. Now I'm looking at the x values and the y3 values, so the black numbers. When x is 0, y is 0. Going in the positive direction, when x is 1, y is 1/2. Going to do the y values that are whole numbers. So if I go down, when x is 2, y is 1. Go down some more. Okay, wait. When x is 4, y is 2. And when x is 6, y is 3. Then going in the negative direction, when x is negative 2, y is 1. When x is negative 4, y is 2. And when x is negative 6, y is 3. Draw the lines. That gives us y equals absolute value of 1/2 x. Describe how the graphs y2 equals f of 4x and y3 equals f of 1/2 x compared to f of x. We can see that y equals absolute value of 4x is narrower than y equals absolute value of x, and y equals absolute value of 1/2 x is wider than the absolute value of x. Let's pick some points on the graphs. where the y values stay the same. And then let's see what happens to the x values. Going from y to y2, y2 is our blue graph and y3 is our purple graph. Let's look at points on the first two graphs, y and y2, where the y values are the same. I'm going to pick y equals to 8 and look at this point and this point. For y equals f of x, this point where y equals to 8 has an x value of 8. So this is 8 units from the y-axis. For y2, that point has a y value of 8, but the x value is only 2, so that is 2 units from the y-axis. So to go from y to y2, we start with 8 units, and then we go to 2 units. To go from 8 units to 2 units with the same y value, we would have to divide by 4, or you can multiply by 1 over 4. And then let's look at points on y and y3 that have the same y value. Let's look at when y equals 3, and we'll look over here on the negative side. When y equals 3 on the original function, x equals negative 3. So this is 3 units away from the y-axis. And then for the graph y3, when y is equal to 3, x is equal to negative 6. So that means this is 6 units away from the y-axis. Then for y to y3, we go from 3 units on the y function to 6 units on y3. That means we had to multiply by 2 to get from 3 to 6 times by 2, or divide by the reciprocal of 2, which is 1/2. If a point xy lies on y equals f of x, then the coordinates of its image point on y2 equals f of 4x, and y3 equals f of 1/2 x are, for y2 equals f of 4x, we would have xy goes to the x value is being multiplied by 1 over 4, so 1 over 4xy, or we can write that as the x value divided by 4 and then the y value. And then for y3 equals f of 1/2 x. The mapping notation would be a point xy from y equals f of x would go to 2x comma y, or we can write that as x divided by 1/2 comma y. Describe what happened to the x and y coordinates when y equals f of x was transformed to y2 equals f of 4x. So the x values are divided by 4, or multiplied by 1 over 4, and the y values are the same. And then for y3 equals f of 1/2 x, the x values are multiplied by 2 or divided by 1/2. And again, the y values stay the same. State the coordinates of any invariant points. From our graph, we had all of the graphs have the point 0, 0. The only invariant point is the point 0, 0. If your y values are not moving, then the x values are the ones that are being affected. If x values are affected, then you must have a horizontal stretch. The horizontal stretch factor, HSF, is not the value of b, but the reciprocal of it. When you have a horizontal stretch, you multiply the x values by the reciprocal of b, or you multiply them by 1/b. Summary. For a function y equals a f of x, the transformation from y equals f of x is a vertical stretch about the x-axis by a factor of the absolute value of a. If a is less than 0, then the graph is also reflected in the x-axis. And invariant points are the x-intercepts. The mapping notation for y equals a f of x is a point xy on y equals f of x becomes the point x ay on y equals a f of x. Example, we have the blue graph f of x, and then y equals a f of x, where a is greater than 1, multiplies our y values by a, so this peak here would get higher. The x-intercepts have y values of 0, so they would stay the same. Multiplying 0 by an a value is still going to be 0. Then for the function y equals f of b of x, the transformation from y equals f of x, it's a horizontal stretch about the y-axis by a factor of 1 over the absolute value of b. If b is less than 0, then the graph is also reflected in the y-axis, and the invariant points are y-intercepts. Mapping notation, a point xy on the function y equals f of x would become the point x over b y for the function y equals f of b of x. An example, we have the blue graph f of x, and then the red graph is y equals f of b of x, where b is greater than 0. So we divide the x values by b, which would make them smaller. So a point that was here would now be smaller, which would bring it in. A point that was here would be smaller, so bring it in. And then the y-intercept is still the same because x is 0 at this point, and 0 divided by b is still going to be 0. When you are stating that something has a stretch, you have to make sure that you state which axis it's being stretched over. So a vertical stretch about the x-axis by a factor of absolute value of a, and a horizontal stretch about the y-axis by a factor of 1 over absolute value b. You have to make sure you include that part when you are describing a stretch. When you have a horizontal stretch, you multiply the x values by the reciprocal of b, which is 1 over b. That is very important. Make sure you know this. Describe using words and mapping notation how the graphs of the following functions relate to the graph of y equals f of x. A, y equals 5 f of x. So A equals 5. That represents a vertical stretch factor of 5 about the x-axis. Vertical stretches are about the x-axis. Then mapping notation, we'd have a point xy on y equals f of x would become the point x 5y on y equals 5 f of x. B, y equals f of 4x. This tells us that b equals 4, which means we have a horizontal stretch factor of the reciprocal of b, 1 over 4, about the y-axis. And mapping notation, a point xy on y equals f of x would become the point 1 over 4 x y on y equals f of 4x. We could also write that as x divided by 4 y. C, negative 1 over 3 y equals f of x. We want to move this negative 1 over 3 over, so we would do that by multiplying by the reciprocal, which would be negative 3 over 1 times negative 3 over 1. Then our 3's divide out, and our 1's divide out, and our negatives divide out, and we're left with y equals negative 3 over 1 f of x, but I don't need to write the 1, so negative 3 f of x. Our a value equals negative 3. Then we have a vertical stretch factor of the absolute value of a, which would be 3 about the x-axis. And a is negative, so we also have a reflection across the x-axis. Then a point x, y on y equals f of x would become the point x negative 3y for the function y equals negative 3 f of x. C, y equals f of negative 1/2 x. B equals negative 1/2 here. That represents a horizontal stretch factor of the reciprocal of the absolute value of b. The reciprocal of 1/2 would be 2 about the y-axis. And b is negative, so we also have a reflection about the y-axis. Then mapping notation, a point xy on y equals f of x would go to the point negative 2x y. The graph of the function y equals f of x has been transformed. Write the equation of the transformed graph. We can see that the shape changed. So we must have a stretch. We could have vertical or horizontal stretch. We could have both. There's no shift because our vertice, the minimum point for both graphs, is in the same place, so there's no shift. There are different possibilities for the equation. Let's say that we have a vertical stretch. I'm going to pick a point on each graph where the x value is the same. So if I look at x equals 6, then this point here is y equals 6, so that's 6 units from the x-axis, and the point on g of x that has an x value of 6 is 18 units away from the x-axis. So I have the point 6, 6 on the original function, and that's going to go to the point 6, 18 on the new function. Our x values are the same, so we can write the mapping notation. xy goes to x, the x values didn't change. The y value, 6 to 18, you'd have to multiply by 3, so that's 3y. That tells us that a equals 3. Then our original function is f of x equals absolute value of x. So the new function we can write as y equals 3 absolute value of x. Or we could write this as a horizontal stretch. Let's look at points on the graphs that have the same y value. I'm going to look at when y equals to 12. I'm going to look on the left side. So in the original function, y equals f of x, the x value is negative 12, which is 12 units away from the y-axis. And then on the transformed function, our point that has a y value of 12 is at negative 4, so 4 away from the y-axis. Then the point on f of x, which was negative 12, 12, was mapped to the point on g of x that has an x value of negative 4 and a y value of 12. So mapping notation, xy goes to, the x value goes from negative 12 to 4. So it's 1/3 of the x value. So 1 over 3x. And the y value didn't change. It's still y. This tells us that b equals the reciprocal of 1/3, which is 3. Then y equals absolute value of 3x. I know that a is positive because both of the graphs are opening up, so there's no reflection across the x-axis. B, in this case, could actually be positive or negative. Since the graphs are symmetrical and the center of the graphs are at the y-axis, if I reflected them across the y-axis, they would look identical. So I could write y equals absolute value of negative 3x. Sometimes they might specify where a is greater than 0 or b is greater than 0. And then you know it's positive, but this one didn't specify, so we could have positive b or a negative b. The point 2, 3 is mapped to the point negative 2, 9 after a reflection and a stretch. Describe the transformations. So we have 2, 3 goes to negative 2, 9, which means that x, y goes to negative x, 2 to negative 2 is negative x, and then 3 to 9 means we're multiplying by 3, so 3y. Then our transformations are a reflection across the y-axis to make x go from x to negative x, and a vertical stretch factor of 3 about the x-axis. That brings us to the end of Chapter 1, Lesson 3.